You know that save button you probably click 100 times a day? Well, every single time you hit it, you're kicking off this incredible high-speed journey for your file. It's totally invisible to us, but it's happening constantly. Today, we're going to pull back the curtain and see exactly what's going on under the hood.
I mean, it feels instant, right? One click and boom, it's done. But that single action sets off a wild chain reaction. We're going to follow a file from just an idea inside your favorite app all the way to its safe and secure home on your hard drive.
So, every great journey starts with a plan, or in this case, a blueprint. Before a file can even be a thing, the operating system has to know what it's dealing with. I want you to think of the OS as a master librarian. When a new book shows up, or for us, a new file, the first thing that librarian does is create a super detailed catalog card for it.
See, to your operating system, a file isn't just the words you wrote or the pixels in a picture. It's a structured object. The source puts it perfectly. It's a named collection of related information. And the OS needs to manage all of it. And to do that, it needs a bunch of very specific details, or what we call attributes.
Now, this is basically the librarian's catalog card, broken down. You've got the name that we humans use, right? But the OS, it uses a unique number, an identifier to keep track of things. It needs to know the file type, exactly where to find it on the disk, how big it is, and, this is a big one, who gets to read it, write to it, or run it. And for you tech folks, an application would use a system call, something like stat, to fetch all this metadata. This blueprint is absolutely crucial for everything that comes next. Okay, so our file has its blueprint. Now what? Well, it needs an address. The OS can't just toss files onto the disk wherever it feels like. It needs an organizational system, a kind of digital address book. And believe me, this system has evolved a lot. In the early days, things were chaotic. Seriously, imagine a library with just one massive drawer for every single card for every book. It was a nightmare. Naming conflicts were everywhere. If you wanted to name your file notes.txt and someone else did too, sorry, can't do it. Super simple, but totally unscalable.
So the logical next step was the two-level directory. This basically gave each user their own drawer in the catalog. All of a sudden, you and I could both have a file called notes.txt because they lived in our own separate spaces. This fixed the naming problem and was a huge leap forward in organization.
And that brings us to what we all use today, the tree structure. This is like having a whole library of catalogs with folders inside of folders inside of folders. It's hierarchical, it's flexible, and it lets us organize our digital lives in a way that actually makes sense. It's really the backbone of every modern operating system.
All right, now for the main event. Our file has its blueprint and an address in the system. But how does the actual data, the ones and zeros, get written onto the physical disk? Well, this all happens through a special conversation between your app and the OS kernel, and they speak a language called system calls.
Think of these as the action words of our file's story. An app can't just go and mess with the hard drive directly. No way. It has to ask the OS politely. It says, hey, create a new file for me, or please write this data, or read from this spot. And that reposition step, seek, or lseek in Unix, is so important. It lets a program jump to a specific spot in a file without reading the whole thing. Think about scrubbing through a video file. That's a seek operation in action. And for all you computer science students, this is where it gets really cool. The basic ideas are the same everywhere, but the actual commands, the system calls, change depending on the OS. So create file on Windows is basically the same idea as open on Unix. And you've probably used chmotto on a Linux terminal 1,000 times to change permissions, right? That's a system call. It's all part of this universal language that makes our computers work. So the OS gets that right command. It's got the data. Now what? It has to find a physical home for it on the disk. And this is a huge challenge. How do you allocate that space efficiently without wasting any? Well, there are a few main strategies.
First up, we have contiguous allocation. Go back to our library. This is like trying to find one single, super long empty shelf that can fit your entire encyclopedia series all in one go. If you can find it, reading is incredibly fast because it's all right there together. But the massive downside is finding a big enough empty spot, which leaves all these little unusable gaps everywhere. We call that external fragmentation.
Next, we have linked allocation. Now, with this method, you can put the volumes of your encyclopedia on any free shelf anywhere in the library. Each volume just has a little note on it that says, hey, the next volume is over on that shelf. This totally gets rid of fragmentation, which is awesome. But if you want to find volume 10, you have to start at volume 1 and follow the chain, which can be really slow on an old-school spinning hard drive. Of course, on modern SSDs, this penalty is way, way smaller, which has really changed the game. And finally, there's indexed allocation. This is kind of the best of both worlds. Here you have a master index card for your encyclopedia, and this one card lists the exact shelf location for every single volume. So you can still put the books wherever there's space, but you can also jump directly to any volume you want just by looking at the index. It's fast and flexible.
So what's the big takeaway from all this? It's that everything is a trade-off. Speed versus storage efficiency, simplicity versus flexibility. This is why modern file systems are so smart. They often use a mix of these strategies, a hybrid approach, to give us the best performance, especially now that they have to deal with both old hard drives and new SSDs. Now, for any of those allocation methods to work, the OS has to do some serious bookkeeping. It has to know at all times which parts of the disk are free and which are occupied. This super important background job is called free space management. One of the most common ways to do this is with something called a bit vector, or a bitmap. Just imagine our librarian has a master list of every single shelf in the library. If a shelf is empty, it gets a 0 next to it. If it's full, it gets a 1. So when the OS needs to find a free spot for a new file, it just scans this list for the first 0 it can find. It's pretty simple, but really effective. And the bit vector is just one way to do it. The OS has other clever methods, like creating a linked list of just the empty blocks, or grouping them together. Each one is just a different strategy to solve that same fundamental puzzle. Where on earth can I put this new data? All right, we are on the home stretch. Our file has been created, it's been organized, and it's been physically saved to the disk. The final step in its long journey is protection. Now the OS has to put on its security guard hat and make sure that only the right people and programs can access that file. This slide really breaks down the different levels of permission the OS can give out. Can you only read it? Are you allowed to write to it or change it? Can you execute it like a program? These controls are what make a multi-user system possible, so that people can't just go around deleting each other's important stuff. And this quote from our source material really just nails it. Protection isn't some feature they tack on at the end. It is a core, fundamental job of the operating system. These security mechanisms are there to enforce the rules and protect the integrity of the whole system. So, the next time you hit that save button, just take a second to remember the incredible, invisible dance you just started. It's a journey through blueprints, digital address books, and security checkpoints, all happening faster than you can blink. We've uncovered the secret life of a file, but what about the life of a process, or the hidden secrets of memory management? Let us know what you want to dive into next time. Thanks for joining me.